Alright, so here we go. Okay, so before we start our MapReduce, I want to, take you through logical steps that how did we end up with Hadoop MapReduce. Okay, so let's go step by step, and as we go forward, you will actually understand the purpose of all of this. Okay, so before we start, so question to all of you is, let's say if you have the plain text file containing all the words of Lord of the Ring books, how would you find the frequencies of the words? Meaning, how many times a has occurred, the has occurred. What are the basically you have to find out unique words and what is the frequency of the unique words, each of the unique words. All right. So question is quite simple. We have to count total number of distinct words in the plain text file. All right. So here, let's say the plain text file is only 50 MB containing the books, and all you wanted to know is what are those most frequent words or least frequent word, or kind of find out the frequency of each words in this particular fiction. The use case of such kind of exercise are many. For example, at Amazon, we used to display the character plot. And the way we used to do is we used to count number of words in the book and remove dictionary words out of it. So the words which were left were generally the characters or the person or the place. Okay. So generally the top words, most frequent words that come out of the fiction is the name of the people, and using this we could always figure out that who are the protagonist or who are the main character in the plot. All right, and there are many more use cases. For example, just by doing the word count we could predict, or character count we could clearly predict that which language are we talking about, what language are they in a book written in. Okay, so the character frequency, word frequency are very important aspect of plain text. All right, so question to all of you is, let's say you are given a huge file. Let's say you're given a plain text file and you just have to find out the unique words and their frequencies. Okay, or distinct words along with their frequency, how many times a particular word has occurred in a book. All right, so the most first approach which we come up with, that we will write a program to do so. Okay, and writing a program is quite simple here. Then let's just create a table. A hash table is like a something like a dictionary. Dictionary, you know what does it mean by dictionary? Dictionary contains lot of words, and along with each word there is a meanings of that word. Okay, so there's a word and the meaning. All right, that's a dictionary. In a similar way, you could create a dictionary using any programming language, be it Java, be it Python, be it PHP, be it Perl. Every language supports this kind of a hash table. All right, so using hash table, you could put, it's a data structure which contains a collection of key and value. The way in an array you have index, at that point of index we have some value. In the similar way, the index in case of dictionary is a string instead of a number. Okay, so we create a index which will contain the word as the key, and the value will be number of times that word has occurred. Initially this dictionary will be empty, and as we iterate through the words, we will keep on updating. We'll keep on looking for each word in the dictionary and keep on updating or incrementing its value. Okay, so the key in the dictionary is the word, and the value in the dictionary is number of times it has occurred. Initially the dictionary is empty, so all you do is you first create an empty dictionary. Then for each word in the file, Check if the word exists in the dictionary. If it does not exist, then the default value is 1. And in case it exists, we increase the value and save it back. And this way, we keep on doing it unless we keep on doing it till the point all words are finished in the file. And when there are no more words left in the file, then we print what is there in the hash table. That's it. That's it. In the hash table, it's a collection of words, and we print it out, showing that which word has occurred how many times. Now, do you see any problem with this approach? The main problem in this approach is that it cannot process the data that does not fit in the RAM. Second, we are not taking the benefit of multiple processors available on your machine, and also we are not taking the advantage of multiple computers if available. But that's okay. Right now, the biggest concern we have is that it won't fit in the RAM, because as I told you earlier also, so whenever out of all the resources in your computer, the first resource that becomes a bottleneck is your computer's RAM. Okay, the first thing that you exhaust is the RAM, the random access memory. Okay, the memory of the computer. Generally, the memory is like 4 GB, 8 GB kind of, right? It's not 100 GB. 100 GB is disk. All right, coming back to it. So the first thing that will become the bottleneck is the memory. You cannot process the data which does not fit into the memory. The dictionary which we have talked about is in the memory. Okay? And in case we try to put the dictionary into the disk, looking up each word in that kind of dictionary will take lots and lots of time. Okay? So, this kind of problem is not solved because it's taking too much RAM. Also, it is not utilizing the computer properly. All right? So, now let's talk about another kind of approach. Okay? So, the second approach, which we do day in, day out, is that we'll take the whole file, break it down word by word, and put it into the database such that each row has only one column and that column contains one word. Okay, so you wrote some program, or in some way you imported all these files into the database such that every column is every column contains one word, or maybe you made it such that the row contains the full line, and then you did a split and all that kind of things that you could do with SQL. Now, here, SQL database has been designed to handle the index which does not fit into the memory, or SQL database can handle the group by on the data which is not fitting into the memory. Correct? Almost every database is designed to utilize the disk and the RAM efficiently in order to handle bigger data than what fits into the RAM. Okay, so this is the approach number 2, where we break down the books into one word per line, one word per row, and insert one word per row into the database. And once you have inserted this full text file into the database, all you need to do is select word, comma, count star from the table and group by the words column. Okay, this is the approach number 2. So the first approach which we talked about is the memory kind of problems, where it basically overflows the memory. The dictionary which we created is an in-memory data structure, and it will overflow. Okay, so we move to next approach, and the approach is SQL. And SQL is well known to handle the data that is not fitting into the memory. The third approach, we could use Unix. All right, so let me explain what it does. All right. So I think we had talked about pipelining earlier. Okay. So cat my file. Okay. It'll print the data, whatever is there inside this file name called my file. And that data, when it prints to the standard output, will be piped to SCD. And what is SCD? SCD is like Control F. Control F, as in you replace one word with another in the incoming stream. So SCD will replace one word with another in the input given to SCD. Okay, so here it says that replace everything which is space or tab any number of times. This regular expression means tab or space any number of times. Plus means many times. Square bracket says that space or tab. Okay, slash t is tab, space is as such. So this means we are trying to replace space or tab any number of continuously with slash n. Okay, which means what are we trying to do is we're converting the text into one word per line. Okay, once we have done that, once we have broken down the text, what we are trying to do is we are sorting the data. What does sorting means? Sorting means we take the input file, order it as in the ascending order. Now, mind it, the input given to the sort command is the output of SED, and SED is converting the full text into one word per line. Okay, now let me start with a very simple situation. Okay, so let me log in. All right, so do we have a file here? All right, let me take some data. Let's say this one. Okay, let's say this file B contains these 6 words, and I want to order the data inside the B file. So what would I do? I'll say cat B. Okay, cat B printed everything on the screen. Next I did was I'm replacing SCD with space or tab any number of times. Okay, and replace with new line and say globally. Okay, but for that I think we need all right, yes, minus E does the job. Minus E does the job. Okay, minus E basically makes sure that it SED understands the regular expression. All right, so here we go. So we were able to convert the input file, which is the output of B we have given to SED. And remember, SED has not changed the file B. It has only printed it to you. Now, the output of SED we can further give to sort command. Okay, in case your data is really huge, you could say sort minus s and 1 gigabyte. It means consume only 1 gigabyte memory. Okay, so now you can see that the data is ordered here by alphabetically or by using the actual values. Okay, so the sort command gave us this result in the sorted manner. The next thing is we run a command called unique. So we are going step by step. Now, if we say unique minus C, it's going to do the job. Now, you might ask, when there is a command called unique, what's the point of sorting, right? What's the point of sorting when you have a command like unique? The reason is unique expects the data to be ordered. It gives wrong result if the input data is not sorted. All right. Now, question to all of you is that the approach number 2 and 3, SQL and this one, these two approaches, do you see any problems? So we talked about earlier where we were loading everything into memory and trying to count the words. In the second and third approach, we were using the systems such as SQL, which basically tries to do the work even if the data does not fit into the memory. Okay, so using SQL or Unix sort command, we were able to count the words which may not fit into the memory. Okay, okay. So we alleviated one problem called RAM. Now we uh, in these two approaches there are many things that become the approach. Okay, so in the approach number 2 and 3, the SQL and the Unix, although we have no longer the RAM as the bottleneck, but as the data keeps growing, the disk speed becomes the first bottleneck, and the second is CPU. First question is, can you read the data from the disk which can be processed at the same time? Okay. Now, if it can be processed, then the processor will become the bottleneck. Okay. So there are many things that will become bottleneck in the approach number 2 and 3. As soon as the data grows beyond tens of gigabytes, what happens is there's a lot of time required to read the data from the disk. As well as when the data is little huge, it takes a long time to sort the data, because sorting in an intensive process, you have to arrange all the words, okay, and then do this, okay. Internally internally sort, as well as the SQL process, the Unix command as well as the SQL command, they are trying to utilize the disk by slicing the data into the parts. Only some part is loaded into the memory and so on. Okay, so these two approaches are cleverly utilizing only small portion of the RAM, but they're utilizing a lot of disk speed, writes and reads. So as the data goes to 10 gigabyte, okay, the time taken to read the data from the disk is for 10 gigabytes is around minimum, it's around 50 seconds. Okay, and similarly at the same time as the you keep on reading the data, it is going to block the CPU, and a lot of CPU will be consumed in ordering the data. So CPU, disk speed, disk space, all these three things will become the bottleneck. Okay, because for sorting 50 gigabyte data, you need 50 extra gigabyte space so that you could split this data into 50 small files and then sort it, right? So disk space, disk speed, and CPU, all the three things will become the bottleneck, right? Now, what can we do to solve this problem if the data is in, say, 50 gigabytes or, say, 100 gigabytes? We are not even talking about terabytes yet. We are talking about, say, we have got now 100 gigabyte text. We want to order it. What will we do? So, one approach is that we use an external sort. One approach is that we use an external sort. What does it mean? We split the files to a size that fits into the memory. Okay, we break down the files to a size that fits into RAM. Okay, next we use either of the previous two approaches to find the frequency and merge sort. Okay, so how do we do this? Using by splitting the files and transferring over a computer, and then get it done on each of the each of the machines. Okay, let me explain this. So let's say you are on the machine called launcher. Okay, and you have got two machines, machine 1 and machine 2, or maybe launcher is also one of the machines. Okay, now what you do is you split the data into two parts. Okay, one part goes to machine 1, other part goes to machine 2. Now you use any of the approaches which we have discussed earlier from 1 to 3 and sort the data on machine 1 and machine 2 and give the result back to the launcher. And once launcher receives the data from both the machines, it will merge the data and keep it sorted. Merge the data and sum up the frequency of all the words. And that way it will give you the result. Now, if we have multiple machines, we have utilized those machines in sorting the data. All right. And in case you are wondering how would we merge it practically without writing code, you can use sort minus m. Okay, in practicality this approach we used a lot earlier before Hadoop came into play. We basically slice the file using one Unix command. One file we sent here, other file we sent here, and once both these machines are done, then we pull it back and then do the sort minus m. Sort minus m basically merges the two files, assuming the two files are already sorted. All right. The problems with the approach number 4. First, there's a lot of time consumed in transport of the data. At least the data from one side, at least the data from one side is unnecessary. If you recollect, we are using HDFS in Hadoop, and in HDFS data is already distributed on many machines. Can't we use the data which is already there? Why do we need to push the data from launcher to anywhere? All we have to do is once we'll just put the data into HDFS and then we launch our work. Okay? And that's where MapReduce comes into play. Alright? The other important aspect in this case is the example which we were giving, that is little too much work. Every time you have to do something, you have to take care of many more situations. Like machine 1, machine 2, one of them went down and we have to send work to somebody else, and so on. There's too much of work involved, and every time we do the computing, we have to write the sorting algorithm, and we have to manage all the network failure, connectivity failure, machine went down, and all kinds of engineering we have to take into account. This is what MapReduce solves for you. So what exactly is MapReduce? It's a paradigm. It's a programming paradigm. Like the way in SQL you have group by, and we just discussed pipelining, and in the same way here, like we have other programming paradigms, here we have a map and reduce kind of a paradigm. So it's a paradigm to solve big data kind of problems, specifically sorting intensive jobs which need the distribution. Okay, any work that can be solved by using multiple machines at the same time can be solved using MapReduce very well. Okay, you would have to write two functions. One that decides what is the key for sorting. Okay, for each record, what is the key on which the basis of which the data gets sorted? That is our mapper. Okay, so you will have to write two functions, or you have to give two programming units or two programs to MapReduce, saying here is my logic for selecting the key for each record, on the basis of which we are going to sort, because sorting could be in many ways. First sorting could be numeric. Sorting could be we want to do it lexically, the way it's in the dictionary, meaning in case of numeric 10 comes after 2, but in case of lexical 10 comes before 2. All right, lexical as in like a dictionary. You remember SAN will come before Sandeep, SANDEEP. Okay, SUN will come after SAN. So in case of dictionary, so there could be many more ways of sorting the data, right? So that's what is the duty of mapper. The mapper gives key and the value, key and the value, key and the value. That's all. Your logic, given an input record, it has to convert that input record into key and value. That's what is the MapReduce. In case of map, we split the data into key and value. Okay. In case of mapper function, and reduce gets all the values aggregated, and the journey from mapper till the reducer happens through Hadoop. Okay, so let's look at this way. Hadoop asks you, give me mapper code and reducer code, and also tell us what file do you want to sort. Okay, all right. So we'll go into more details just after this slide. So basically, you have to code two functions called mapper and reducer. Mapper, which converts the input into key and value, and reducer knows how to combine multiple values for each key. If there are multiple values for each key, you'll get reduce in the reducer, and reducer can aggregate that and return it. All right, it's like saying group by. It's like a grand group by. In case of group by, we define that hey, this is a column on which we want to group by, and we define an aggregate function. These are the two things we do as part of group by. In case of in SQL, we write group by. In the same way, here is mapper reducer. Rest of the things is taken care of by Hadoop. All right. Now this paradigm is not specific to Hadoop anymore. Okay, it's not specific to Hadoop anymore because MongoDB, CouchDB, Cassandra, and all of these databases, new generation databases, are using the same paradigm. Spark uses a similar paradigm. All right. Similarly, this code mapper and reducer could be written other than in Java using something called Hadoop streaming. We'll talk about Hadoop streaming before we talk about Hadoop in Java. All right. So here we go. So you imagine for time being, you see this function here? This is the code you have written. This is the code you have written. Okay? So you tell map and reduce that, hey, here is my code for mapper and here is my code for reducer. And this is the file we are trying to churn. So what mapper and reducer is going to do is they'll pick the input file. For each line in that input file, your function is going to get called. And this function is telling that this is my key and this is my value. This map function is giving out all the possible key values for every record. Okay, if there are 50 lines in the input, this function is going to be called 50 times. Okay, and for each line is going to give out many key values. Okay, so it's saying that sa1, re1, sa1 again, and ga1. That's all map function is giving out. It's not doing anything else. For every line, when the map function gets called, it's going to split the input line into words and then print out word comma 1 for every word. Okay, then this gets converted magically into this by Hadoop. Okay, you see this dash line, you see this line. This means Hadoop is doing the sorting and doing the unique minus C, is basically bringing all the keys together, all the values for a single key together. For you see here, for ga it's 1, for re it's 1, sa 1 comma 1. Okay, so Hadoop has brought all the values for each key together. Now, how to combine these multiple values into a single value is something done by reduce function. Okay, so output of the reduce function is a single value out of the multiple values. Okay, it's up to the reduce function what is it that it wants to give out. Okay, reduce function will get how many times the reduce function get called? Reduce function will get called 3 times because there are 3 keys here. Had there been 5,000 keys in the input, reduce function will be called 5,000 times. Is that clear? So basically the role of mapper is break down things into key value such that Hadoop can sort and group the data based on the key. And for each key and all the values, the reduce function can be called. Okay, and reduce function decides how to aggregate. It is exactly like SQL's group by, where you decide that from the input table, let's group the data based on a particular column, and then in the reduce and then aggregate. Again, it's not mandatory always to give reduce function. You can say, hey, my thing does not have reduce function at all. Then Hadoop will not do these parts. Okay, so mapper always give out the key and value. All right, now imagine the same logic. You wrote the logic once and that's it. You did not have to do anything else. You wrote your this particular logic, and you did not have to worry about how will the data get transmitted, how will we read from HDFS. Nothing. That is done by Hadoop. The way you do not worry about internals of SQL while writing group by clause. In the similar way, you do not worry about internals of sorting and other things while writing MapReduce, because sorting is the duty of MapReduce. Dividing the work, dividing your work to multiple machines is the duty of MapReduce, and getting that executed is the duty of Hadoop Yarn. Yarn. All right. Now look at this. Imagine that you had two parts of a file. Part 1 on one machine and part 2 on second machine. So the work will only be sent to those two machines. Though only those two machines which contains the two parts of the same file. Those two machines will be selected. In case there are 50 such machines, meaning a file containing 50 different blocks, and these 50 blocks are located on 50 different machines, then there will be 50 machines instead of two machines. Okay, so right now we have only hardly say two blocks of data, one on one machine, other on another machine. Only these two machines will be selected for the work. And then these two machines, on these two machines, for every record or for every line, your same mapper function will get executed. Okay, here I was trying to show you in case your file is really small. Here I'm trying to show you in case your file has two blocks, and two blocks, one on one machine, another on another machine. In those cases, there will be two machines will be running the map function, and this map function will be executed for every line. There are, let's say here there are 100 lines and there are 500 lines here. So 100 times it will be executed on node 1 and 500 times it will be executed on the node 2. And node 1 and node 2 will give the results, and the sorting will happen on node 1 and node 2. Okay? And once that is done, there will be a step for merging the data from both the nodes, and after that merge has happened, then for each key reduce will be called. If there are 10 only 10 keys, then reduce will be called 10 times. Okay, now after reduce function has been called on every key, the result will be saved in the output like this. All right. This way of looking at MapReduce also makes a lot of sense. So imagine that this is your first part of the HDFS, second part of the HDFS, third part of the HDFS file, I mean. So you had a file which got broken into three parts, three blocks, and those three blocks are located on three different machines. 1, 2, 3. Now, first one gets loaded into something called input split. Okay, so for every line in the block or every record inside the block, your map function is going to get called, and the result of map function is being sorted here. And whatever is the output, it gets taken to this reducer node as and when the mapper is mapping and sorting is happening. And after sorting is done, the data will get copied to a central location. And once that is done, the merging will start happening of these parts. Now, at this point, in case these two were successful, this one failed. This will get executed on another machine, and the same process will again start. And so because merge needs all the parts from all the machines. In case this one failed, then this one will get executed on another node containing the same block. Okay, so generally this transfer is local. It will try its best to execute your map function very near to the block. Otherwise, a lot of time will actually go into transmitting the data from one node to another. And once it has merged the data here, then the reduce will execute. Okay, right now there is a single reducer. Okay, and the output of reducer is being saved in HDFS. Okay, the output of the output of the reducer is going into HDFS. All right, sometimes you might choose to go for multiple reducer. What if this reducer is not sufficient? What happens is that, let's say this reducer is not sufficient, it's getting overloaded. You can tell Hadoop that, can you please execute two reducers, two reducer nodes. These are called reducer node. This is a reducer function. Okay, the machine which is running the reducer is also called the reducer. Function is also called the reduce. Okay, so if there are multiple reducers, what happens is the output of the mapper is broken into two buckets. Output of the mapper is broken into two buckets. First one goes to first reducer, second bucket goes to the second reducer. Okay, so whenever you run MapReduce, you run MapReduce on top of an input file. You say to Hadoop that, hey, this is my input file. This is the logic for mapper, and this is the logic for reducer. Okay, this is the logic for mapper, this is the logic for reducer, and I want these many reducers. If you do not specify a number of reducers, by default Hadoop MapReduce assumes the number of reducers as 1. Okay, if you specify that, hey, I want 20 reducers, then there will be 20 reducers. And every mapper node, instead of creating one output, one sorted output, it'll create 20 such buckets, the way it has created two buckets, such that first bucket goes to first machine, second bucket goes to second machine. Now question here remains that on what basis does it do this? It's based on the hash code. The key gets converted into a number, and that number is divided by reducer nodes. Okay, so that the remainder is always less than total number of reducers, and that's what decides which reducer node is getting called. Okay, so basically it's kind of deciding based on certain number. Okay, so every key gets converted into a number here, and based on that number we decide whether to send it on this or this. Here, whosoever key is, say, even, that will be put into one bucket. Whosoever key is odd will be put into another bucket, and that's how this division of the data happens. Okay, so right now what you see here is that there is a data transport involved in case of more reducers. If there are more reducers, earlier there were one reducer, so there was only three transports happening. Now there are two reducers, that means there will be six transports happening. Okay, six transports will happen because the data from each of the mapper node will go to both the reducers. Okay, and that's how the map and reduce actually work. All right, so as I've already told you, that map reduce is very analogous to group by. So select star from count and group by this. Okay, group by this part is actually this, and count star is this. Okay, count star gets executed for every word, and that's how reduce gets executed for every key. Okay, so now let me describe that command again, the one which we did earlier. Yeah, this is the one which we did. We said, okay, let me try to bring it to a bigger font. All right, so you can see here the first is Hadoop command. Okay, first is Hadoop command, and then is this jar. Instead of saying Hadoop fs, we are saying jar, which means we want to execute this logic as MapReduce. Okay, this is the logic called Hadoop MapReduce examples. What does it have? It has source code. It has this Java compiled logic of word count. Okay. The first argument we are telling it is the word count. Okay. Now, here you can see that we are providing an input folder. Okay. So we are telling Hadoop that here is my input files. Okay. And we are providing the output folder. Where should it keep the output data? Okay. Let me just, if you try to run it again, it will give an error saying this folder already exists. It says that mrout6dab is already existing, and it's trying to create this folder in my home directory in HDFS. Okay, so let me correct it. Let's just check if it gives an error and runs it successfully. Now it's trying to run it again. You can see the URL to track the job is here. All right. So let me just see MapReduce examples source code. Okay, although I have ready, okay, can I just show you quickly? Although I will get into the details again in case of Java, I want to show you how does the MapReduce example looks like. Okay, I want to show you here. All right, so what exactly did we do here? We executed this command called Hadoop jar, provided this library, you see here, from here to here. This is the name of already somebody has written a code for doing the word count. This code contains two pieces of logic. One is called mapper, other is reducer. And in this also it is mentioned that who is my mapper, who is my reducer. Okay, and then we specify the first argument as word count, which is something this is expecting. We specify that this is our input folder and this is our output folder. Okay, right. As a quick example of my code, although you can see it in the example. All right, here we go. All right, so first of all, I want to show you. Yes, this is a word count example. In the same way, you see here we have written a mapper function. Don't look at any other piece of code. Java makes it look little ugly. Okay, so here what are we trying to do? We are trying to, what did we get in the map function? We got the input line. Okay, input line, this is the value, the input line, this is the line number, the byte count basically. And then we have to do something with the input line. All we did was we cleaned up input line, we split it on the basis of a space, and then we, for each of the words, we removed everything which is non-alphanumeric, and then we converted it into lowercase, and then we printed it in the key value format. Okay, so this piece of code, what is it doing? It's outputting key and value. It's saying this is my key, this is my value. For each of the words, it iterated and it has given, this is basically nothing but one, this is one, and this is the key, which is each word of the input data. So the most important part is this is the code you write. Okay, but it is constrained means it is supposed to only take this as the key, this as the value, and then do something about it, and whatever it wants to give out, like key value, it gives out using context.write. And similarly, you will have to write another class called reducer. There you will define a function called reduce, in which you will be given key and the list of values. You see, it is the list of values. It is an iterator. That's so in reduce you got key and the list of values. All right. And then you do something about it. Here we are trying to sum it up. Okay. Imagine that you are defining a function. Let's say you write a function, my function, or you can say my map function. Okay. You will get kind of a key in the input, and inside it you will be writing your logic. You will be saying uh, generate key comma 1 or key comma some value. So you will create the function called mymap. Then you will create something called MyReduce. Okay. In this you will get key and array of value. Okay. And here you will write some logic. So basically you are creating two functions. One is mymapper and one is reducer. Okay. And then you will say, while calling the MapReduce, you will tell that here is my mapper, here's my reducer, this is the file I want to churn, and these are the things I want to do. Okay. So here, in case of word count, what are we trying to do? The key, the input we are getting is a line. Okay, for each line, your map function is going to get called. And what are you trying to do? You're trying to say for word in line dot split. Okay, I'm trying to write a very simple pseudocode. Okay, and then inside this, I'm trying to say print word comma 1. Okay, this basically we have splitted the line into words, and for each of the words we are printing this, or you can say generate this. This is a pseudocode I'm trying to say. Okay, so in case you are not in touch with the coding for quite a while, don't worry. So here I'm trying to simplify that. What is the role of this function? You're supposed to write such a function called mapper. This is your mapper function, and in the reducer you will get you say kind of array of values. Okay, so here we are saying int sum is equals to 0, and for value in array of values, I'm saying sum plus equals to v. Okay, and then I'm saying return key comma v, key comma sum. Okay, so you see that these kind of two functions you have to define. All right, and that's the kind of thing that's happening right now. Okay, so basically in here you can see that the job is running and it is finished. All right. Okay, so here the problems have decent amount of difficulty. So first problem is, instead of doing the word count, if you had to do the frequency count for each letter. Okay, again, frequency count is used in many ways at many places. Okay, so my question is, would you use MapReduce? If so, in what circumstances you will use MapReduce, and how would you write your MapReducer code? Or I'm looking for this kind of a pseudo code. You will get line in the input, okay, and each line contains the text, and then you have to write your reduce function like this and mapper function like this. Okay, this is the kind of format I'm looking for. Second question is, you're given a huge text, okay, and you have to find anagram in this huge text. An anagram is basically a different arrangement of the letters. Okay, so in this text, bring together all the anagrams. bring together all the words which are anagrams of each other. For example, let's say the input text is the cat act in tic-tac-toe. So here, act, cat, and tack. These three words are anagram of each other. They are brought together in a single line, while the other words do not have anagram present in any of this. Okay, anagram is just different arrangement of the letters. Okay, so the does not have anagram. If there was here there was one word called cit, that then cit will come together with tic. Okay, so given a huge text, you have to find out all the anagram present in the text. Okay, you have to bring together all the anagrams. All right, these are the two questions. Third is, let us say that you are given a text file which contain the login and the DNA of the person. You have to bring all those logins together, all those users together whose DNA is identical. You have to find people whose DNA is identical. The third B problem is, some scientists came up with this hypothesis that, or some scientists came up with this idea that, or some proof that if two persons have identical DNA or mirror image of DNA, okay, then those two persons belong to the same family. So you have to bring people together who belong to the same family. You have to bring all those people together who belong to the same family. For example, here, user 1, user 2, and user 4. User 1 and user 2 have exact mirror image, ACGT. ACGT. You see, it's just reverse of user 1. User 1 and user 4 have identical DNA. Therefore, user 1, user 2, and user 4 belong to the same family. You have to bring these users together. Some scientists came up with this research that please bring the DNA together. All right? So you have to do that. Okay? So fourth problem is that in this unusual democracy, the people who has more wealth are considered uh, as their vote is counted more. If you have say $1,000 with you, that means your vote will be counted as one. 2,000 means two, and so on. So here you are given as a worth of the people in one file, and who voted for who in another file. Okay, you are given two files, one containing who voted for who, and second containing the worth of people. Now, the vote count of a person is equal to the sum of the worths of all the voters. Okay, for example, C was voted by A and B, so C's worth is A plus B, which is 6. Okay, F was voted by C and C's worth is 11. Therefore, F's vote count is 11. So you have to, given these two files, you have to find out their vote count. And please note that if you put list 1, list 2 in a single folder, and you can feed them to MapReduce in a single way. All right. Okay. So one is, you can go to here and say, here, this is the one I'm talking about. In the session number 3, there's a MapReduce subjective test, subjective questions. Okay. All right. See you then.